Section: Introduction. In this section, we discuss differentially private mechanisms that handle sensitive user data to perform computations while safeguarding user privacy. One common mechanism involves creating a synthetic version of the input dataset, which can be used for various tasks like training machine learning models or other data-related activities. Recent interest has emerged in using large language models, LLMs, to generate differentially private text datasets. These approaches can be categorized into private fine-tuning and private prediction methods. Private fine-tuning adjusts the LLM parameters on the input data using techniques like differentially private stochastic gradient descent and then generates similar text. While this method produces high-quality synthetic data, it requires significant resources to train large LLMs. On the other hand, private prediction methods do not modify the LLM parameters but prompt the model with input text and perturb its token distribution to ensure privacy. This method is faster but may not guarantee strong privacy when generating large amounts of data. We introduce a new private prediction method that can generate significantly more synthetic data while maintaining privacy. Our method involves running LLM inference on subsets of the input data in parallel and aggregating their token distributions to create synthetic text. We improve performance by leveraging sampling uncertainty for privacy, clipping and aggregating token logits, and using fixed subsets of input data for generating synthetic examples. By incorporating these techniques, we achieve better results compared to existing methods. Our experiments involve generating private synthetic datasets from benchmark machine learning datasets and using them for classification tasks. We outperform existing methods in terms of downstream accuracy and demonstrate the ability to generate thousands of training examples. Additionally, we evaluate data quality by preserving data structure in synthetic datasets, showing promising results at high privacy levels. Section Summary. In this section, we introduce differentially private mechanisms that process source datasets containing sensitive user information to perform computations while safeguarding user privacy. We discuss private fine-tuning and private prediction methods using large language models, LLMs, to generate synthetic data, highlighting the trade-offs between training time and privacy guarantees. Additionally, we present a novel private prediction method that significantly increases the amount of synthetic data generated while maintaining privacy, showcasing improvements in downstream accuracy and the ability to create thousands of training examples for fine-tuning models. Section: Related work. In this section, we will discuss the related work on private fine-tuning for synthetic text generation. Private fine-tuning is a common technique used to generate synthetic text. It involves adjusting a large language model, LLM, using differential privacy stochastic gradient descent, DPSGD, on sensitive data to create private synthetic versions of text datasets. By using parameter-efficient methods like LoRa, the quality of synthetic data can be improved by reducing the number of parameters, which in turn reduces noise during optimization. A two-stage approach is often taken in private fine-tuning. Initially, the LLM is fine-tuned on a public dataset similar to the sensitive data. Then, DPSGD is applied to fine-tune the model on the sensitive dataset. Private prediction is another approach in private machine learning that focuses on ensuring the privacy of model predictions rather than the model itself. This technique has been applied to synthetic text generation by treating each token sampled by the LLM as a prediction and perturbing the token distributions for privacy. Private filtering methods work directly on LLM responses and a large corpus of public data without needing protection. These methods select similar responses from the public dataset based on sensitive responses. However, one limitation is that the range of possible responses is determined without input from the new dataset. Moving on to the method section, we review the standard algorithm for LLM inference. The LLM is a function that maps token sequences to logit vectors, which are used to generate responses. The algorithm involves drawing tokens based on a probability distribution until a special token indicating the end of the response is reached. Our algorithm focuses on privately generating synthetic text from sensitive prompts. Instead of using a single prompt, we use a batch of prompts to run multiple LLM inferences in parallel. Each synthetic example is generated one token at a time, with the average of logit vectors determining the distribution for selecting the next token. To ensure privacy, the logits are clipped and recentered before averaging. We also incorporate a non-sensitive public prompt to minimize privacy costs when selecting tokens. The privacy guarantee of our algorithm is based on the analysis of sparse vector techniques, showing that privacy degradation is independent of the number of public output tokens. By carefully selecting private and public tokens, high-quality synthetic data can be generated with only a fraction of private tokens. The algorithm partitions sensitive prompts into batches, and while batching approaches can vary, efficient data usage is achieved when batch sizes match the expected size. Tailored batching strategies can further enhance the quality of synthetic data. Section Summary. In this section, we summarize the related work on private fine-tuning for synthetic text generation. Private fine-tuning methods like LoRa aim to enhance the quality of synthetic data by reducing the number of parameters to minimize noise during optimization. Additionally, private prediction techniques perturb token distributions to ensure privacy in generating synthetic text, although a privacy loss is incurred for each token produced. Section: Relationship to prior work. In this section, we will discuss the connection to previous research. Our algorithm has two main characteristics. It uses the randomness of token sampling to ensure privacy and reduces privacy cost by incorporating public data to create synthetic data. Some earlier studies also used similar ideas but with some differences. Instead of adjusting logits for private token sampling, they combined sensitive token distribution with a uniform distribution. This method relied on the vocabulary size, making the privacy guarantee weaker when dealing with large vocabularies. Another approach ensured privacy by mixing sensitive token distribution with a public one, but it aggregated fine-tuned models instead of prompts. Neither of these approaches aimed to generate synthetic data. One study limited the token vocabulary to the top 100 public tokens, which improved stability but struggled with rare tokens in sensitive data. In contrast, our method dynamically compares public and private token distributions to balance privacy and quality when sampling tokens. We also address the challenge of using a single subset of prompts for generating all tokens in a synthetic example, leading to enhanced privacy and computational efficiency. Moving on to privacy analysis, we demonstrate that our algorithm maintains the privacy of sensitive prompts used for generating synthetic examples. We define a mechanism as a randomized function operating on prompt datasets. Two prompt datasets are considered neighbors if they differ by only one prompt. Our algorithm ensures epsilon, delta, differential privacy by controlling the probability of outcomes for neighboring datasets. The proof of this privacy guarantee relies on a technical assumption about how prompts are grouped into batches at the algorithm's outset. By assigning prompts to batches based solely on the prompts themselves, we can ensure privacy. Using hash functions for batch assignment, we can accommodate prompts with shared attributes without affecting the privacy guarantee. For experiments, we utilize Gemma 1.12 bit as the data generator for private prediction tasks due to its lightweight JAX implementation. We conduct experiments across various datasets and utility criteria, including in-context learning, fine-tuning, and structured data tasks. These experiments involve generating synthetic examples for different purposes, such as in-context prompting for language models, fine-tuning BERT classifiers, and preserving structural constraints in data generation. Section Summary. In this section, we introduce our algorithm which ensures privacy by leveraging token sampling randomness and using public data to generate synthetic data. Our approach improves upon prior methods by dynamically comparing public and private token distributions to balance privacy and quality, resolving issues with rare tokens in sensitive data. Additionally, we prove the privacy preservation of our algorithm through differential privacy analysis, showcasing its effectiveness in generating synthetic data for various tasks like in-context learning, fine-tuning, and structured data generation. Section: In-context learning. In this section, we conducted experiments using our method to create synthetic data for in-context learning tasks. We compared our results with previous work that generated only 4 examples for in-context learning. To assess the quality of our synthetic data, we placed these examples in a context window before testing them with real examples. We used GPT-3 Babbage 002 with a 16K context window for evaluation on various datasets. Our evaluation setup closely followed previous work, although some aspects could not be replicated due to changes in OpenAI API access. We limited our evaluations to 64-shot in-context learning accuracy for cost and efficiency reasons, even though our method can generate more examples. Surprisingly, our synthetic data at 64 shots outperformed real data at 4 shots, which is a significant improvement. We also surpassed results reported in previous studies, although there were differences in the experimental setup. Moving on to fine-tuning, we achieved notable advancements over existing private inference methods for in-context learning tasks. Our method can generate a large amount of synthetic data efficiently, raising the question of its competitiveness with state-of-the-art private fine-tuning methods. By fine-tuning 110M BERT base models on various classification tasks, we generated between 2.5K to 200K examples for fine-tuning across different datasets and privacy levels. Furthermore, we explored the limited data regime and demonstrated the effectiveness of our private prediction method in generating useful examples for in-context learning. We also showcased the benefits of using the sparse vector technique, SVT, for structured data, which minimizes privacy loss compared to other private inference methods. In our experiments with JSON generation using a dataset of American movie information, we evaluated the quality of the output in terms of well-formed JSON and basic schema validation. Our method showed promising results in generating structured data efficiently and accurately. Section Summary. In this section, we experiment with in-context learning by generating synthetic data and comparing it to real examples. We evaluate our method on various datasets and achieve comparable results to real data at 64 shots, surpassing the performance of methods limited to generating only 4 examples. Additionally, we explore fine-tuning by generating synthetic data for 110M BERT base models, showing significant improvements over existing private inference methods and achieving reasonable performance on downstream classification tasks. Section: Results. In this section, we present our results. The results can be found in the table. When we aim to generate a large number of examples with small privacy parameter epsilon, we need to increase the sampling temperature tau to ensure privacy. However, this can affect the quality of the generated outputs. For structured generation, there are tokens that are crucial for maintaining the structure and are easy to predict without sensitive data. The Structured Value Transformer, SVT, helps us reliably obtain these tokens at no extra cost, leading to better generation quality. We believe that our significant performance improvement is mainly due to 2 algorithmic innovations. Firstly, we preserve the privacy of the entire distributions from which each token is sampled, even though only the token itself is included in the synthetic data. This is different from the exponential mechanism used in other methods, which require maintaining a differentially private version of the entire token distribution to release a single token, leading to higher noise requirements. Empirically, we achieved good synthetic data quality with specific parameter values. Switching to the Gaussian mechanism for comparable privacy guarantees would require a significantly lower noise magnitude compared to our method. Secondly, generating each token using a different random sample of sensitive prompts is computationally expensive and prevents efficient decoding. Our approach overcomes this limitation by using a fixed subset of sensitive prompts for each synthetic example, allowing us to balance privacy and computation efficiently.